using this generic face model. Because typically the way you find the facial features, the eyes and the boundary of the face and the mouth, is to do some kind of an edge detection or fitting some kind of a closed curve to the face. And given a noisy data or low quality image, that always becomes a difficult thing. So model-driven feature point detection always works much better than bottom-up image detection. And so the use of AAM is to, let's collect, say, training set of 100 face images, mark manually the boundary points, overlay them somehow, and get a generic two-dimensional model for the facial feature points. And now you've given some arbitrary image, I can fit this model to that image and extract automatically the feature points. So that's in a nutshell is what AAM is. And the code for AAM is available in the public domain. So you can download AAM code from a variety of websites. And there's sort of real-time algorithms available for AAM, because you want this process of feature extraction to be in real time. You know, when I say real time may mean different things to different people. But you know, if you want to do face recognition in a video, as an example, you have to do it at the frame rate. And so that's why efficiency of the algorithm is also quite important. The next important thing is the morphable model by glance, and that's basically generates a 3D generic model of a face. So again, going back to the structured light, you get a user-specific model. But what if we take many user-specific models and come up with some kind of a generic model? And the advantage of that is, if I now give you a two-dimensional image, having this generic model helps you build a 3D model which is specific to that particular 2D face. So this involves doing a fitting of 3D model to the 2D image and doing what is referred to as the texture mapping. That is, put that particular person's 2D facial pattern, gray level pattern onto that 2D model. So typically, in many of the difficult face recognition problems, you use a combination of AAM and morphable model to do the recognition. First, you use AAM to detect the feature points, and then you use the morphable model to obtain the three-dimensional shape of the extracted 2D feature points. So hopefully, I'll show you illustration of this later. So this is just an example of active appearance model. And the main thing to keep in mind is what are the feature points. These are the green points. So these are about 70 or so points which delineate the face boundary and around the nose, mouth, and the eyebrows, and so on. And in the training set, these points are marked manually. You build a AAM model from that, and then given a two-dimensional image, this model is automatically fit to a two-dimensional image, and you extract these points automatically. This is the morphable model, and the advantage again is that once you have a morphable model, you can do all kinds of deformation, introduce expressions. So if you want to do expression invariant face recognition, this helps you to do that. So how do you get this morphable model? Well, somebody sits in front of this scanner, and it goes around you to build a 3D model, just like I showed you 5 different views of my student who stood in front of the 5 different viewpoints in front of the scanner. This is the more advanced model which automatically goes around the person's face. And then there are many several models in the database, and you somehow come up with a weighted combination of these models to come up with a generic model. And then this just shows how the morphable model then gets fit to a two-dimensional image. And again, the code for such building the model and the fitting is available on the website. So if you want to use Blank's model, that's available on the website. Typically, it's available in the form of a mesh model. So one of the things we have been working on is how do we recognize faces in video. And The reason why this problem is important, as I mentioned to you, video cameras, surveillance cameras are everywhere, from airports to 7-Eleven and so on. But the problem with these images is that they are generally of lower quality than images captured using, still images captured using CCD camera. There are more pose and illumination variations and they are low resolution. But on the other hand, a video sequence gives you multiple frames of the same person, so you have temporal information, so you have additional information, and somehow that should help you in face recognition as well. So one of the first things we do, this is an illustration of how the AAM model is being used on the video frame. So here you can probably see the blue points which are being fit to the individual video frames. But they're quite noisy, so in order to do a better job, we can do some temporal coherency, that is, in multiple frames, the positions, successive multiple frames of the same face, the position of the points is not changing so much. So using that information, you can smooth out the position of the points. And so now the individual feature points which we detect are not as, don't undergo as much perturbation. So once we can detect the feature points in the individual frames, I already introduced this idea, which probably most of you know about, using the stereo to build a 3D model. So stereo uses two stationary cameras, left image, right image, and you do the correspondence to build a 3D model. You can do the same thing using what is called the structure from motion. So again, when we say structure from motion, it means defining the 3D information from motion information. So in this particular case, individual feature points are moving because you have multiple video frames. And by looking at the correspondence between these multiple feature points, you can build a 3D model. So this, on the left, we are showing the video with feature points tracked. And on the right, we have now the reconstructed 3D model of the same face. And now I can generate that, an image of that model at any orientation I want. So this is a standard database available from Carnegie Mellon University called Face in Action database. And so it's showing the original video of a face. Again, this is still a laboratory data because there is no occlusion and it is taken indoors. But still, it's more challenging than some of the other simpler databases which are available. So at the bottom, we are showing the feature point tracking using AAM, and then we have the reconstructed 3D face model. So here is the way we do the view synthesis. And so typically what happens is the two terms used in face recognition, gallery and probe. By gallery, we mean the database. And in the gallery, typically you have the frontal pose of the person enrolled in the database. Whereas the pose, the viewpoint of the face can be in any arbitrary orientation. So it will be nice if we can correct the probe pose to also frontal, because frontal to frontal matching is more reliable than sideways to frontal matching. So this is what is going on. That in an input video, we have multiple frames available. And from that, we build the 3D model. And once we have the 3D model, we can generate the frontal view. And once we have the frontal view, we can match the frontal view to the gallery frontal view. So this, basically the curve on the right, or the plot on the right, is referred to as cumulative matching curve. And the horizontal axis is the rank at which the correct match